Methyl allyl chloride, MAC, is a chemical used in the production of insecticides. We can see the structure of MAC here below. And we need to give the molecular formula of this compound here. So our molecular formula is our actual whole number ratio of the atoms within the compound. And we can see that we've got carbons, hydrogen, and chlorine within our compound. So let's count up the numbers of the different atoms. So our carbons, we've got 1, 2, 3, 4. That's C4. For our hydrogens, we've got 1, 2, 3, 4, and then that makes 7 there overall. So that's C4H7 so far. And then we've got 1 chlorine. So our overall molecular formula is C4H7Cl, like so. The next part, we need to draw the skeletal formula of MAC. So for the skeletal formula, we show the carbon-hydrogen backbone as zigzag lines overall, so something a bit like this overall. So we don't show any hydrogen atoms at all. We only draw an atom if it's not a carbon or a hydrogen, so a different functional group overall. So let's draw this out here. So we can see we've got 1, 2, 3 carbons as our main carbon backbone. So let's draw that in like that. We've then got another methyl group up here, so we can add this on here. We've then got the double bond to add on between carbons 1 and 2, and then we need to add in our chlorine atom because that's not a hydrogen, so therefore we can draw that in as a bond. For the last part, we need to state what's meant by the term structural isomers. So our structural isomers are compounds which have got the same molecular formula but a different structural formula overall. And the key thing here is to include both of these parts for the mark. So you have to say both parts or you won't get the mark overall. And that's your 1 mark question for this part here. MAC is highly flammable, and when it burns, one of the products formed is a toxic gas. And we've been given some information and we need to identify what the gas is. So we've been told that 1.321 grams of this gas occupies 1.053 decimeters cubed at pressure of 100 kilopascals and a temperature of 350 Kelvin. So with this information here, we can use the ideal gas equation, which is PV equals nRT, and we can use this equation to identify the moles, because once we've got the moles, we can then use our mass in order to identify the molecular mass, which will be equal to the mass divided by the moles. So let's start by rearranging our equation for the ideal gas equation to work out the moles. So our moles is going to be equal to the pressure and the volume divided by the gas constant R, which is in the data book, times by the temperature overall. Now the key thing with our ideal gas equation is to make sure that we're using our standard index units. So this is going to be pressure in pascals, temperature in Kelvin overall, and volume in meters cubed. So we need to make sure that we convert some of our data here above to the correct units. So 1.053 decimeters cubed, to convert that to meters cubed, we just have to divide it by 1,000 overall. So we will have 1.053 times 10 to the minus 3 meters cubed. And then next we need to convert our pressure into pascals. And to go from kilopascals to pascals, we just multiply by 1,000. So therefore we have 100,000 pascals as our pressure. And our temperature is already in Kelvin, so we don't need to worry about converting that. And the gas constant you can find in your data book, and that is going to be 8.314 joules per Kelvin per mole overall. So now we can plug in our numbers. So our moles is going to be equal to 100,000 pascals times by 1.053 times 10 to the minus 3 meters cubed, all divided by 8.314 for our gas constant, times by 350 Kelvin. And if you pop this into your calculator, this will give you a value of 0.0362 for our moles overall. There. So now our next step is to use our moles and our mass, which was given to us at the beginning, to work out the molecular mass of this toxic gas. So the molecular mass is going to be equal to 1.321 grams divided by 0.0362 moles overall. And this comes to a value of 36.5. Now, to try and identify this gas here, we know that when we burn hydrocarbons, we normally produce carbon dioxide and water, and if it's incomplete combustion, we also could produce some carbon monoxide and some carbon particulates. But our compound MAC has got this chlorine atom in it, and chlorine has got an atomic mass of 35.5. And a toxic gas which we've come across before could be HCl. And this has a mass of 36.5 because it's 1 from the hydrogen plus our 35.5 from the chlorine, which gives us 36.5. And that would make sense because we've got a source of chlorine in our compound MAC. Therefore, our gas is going to be hydrogen chloride, HCl. And for this question, there was a mark for the working out with the ideal gas equation, a mark for identifying the moles of the gas, 1 mark for the working out of the molecular mass of your gas, and then the final mark was for identifying that the gas was HCl overall. The flowchart below shows some of the reactions of MAC, which is this compound here. And we need to complete this flowchart by drawing the structure of the product of reaction 1 and the structure of the minor organic product of reaction 2, which is compound B overall. So let's start with the product from reaction 1. We've got our compound MAC here, and our reagents is hydrogen and nickel. And this reaction is going to be a hydrogenation reaction where we open up this double bond and instead we saturate the compound with hydrogen. So our compound will look like this. So we've got our 2 carbons in the middle, we've still got our CH2Cl, our methyl group up here, the 2 hydrogens are from the original compound, and then we're adding on 2 additional hydrogens. So we've ensured that each carbon has still got 4 bonds, and we've now saturated this compound. So it's got the maximum number of bonds that it can get around each atom. We've saturated it with hydrogen. So now the structure of the minor organic product of reaction 2. So these reactions are electrophilic addition reactions, and we've got the reaction with HCl over here overall. And this is going to, again, add on across this double bond. So we can see that with the major product, we've added on our chlorine to this carbon here and our hydrogen to this carbon here. And the reason why this is the major product is because it would have gone via the most stable intermediate. So the intermediate would have been via the most stable carbocation, which would have looked like this overall. So a carbocation is where you've got positive charge on a carbon. And the reason why this is the most stable carbocation is because it's a tertiary carbocation overall. So we've got 3 different carbons bonded to the specific carbocation, therefore it's tertiary. So this is the most stable intermediate. So therefore, the minor product will be where instead we've got the charge on this carbon here, so the other atom from that double bond. So that will look something like this overall. So this time we've added our hydrogen on to the second carbon, therefore leaving us with the positive charge on this carbon here, and this carbon has only got 1 other carbon attached. Therefore, this one is going to be a primary carbocation, which is less stable, hence why it's the minor product overall. So the product will look like this. So it's where we've got the Cl bonded where that charge was, like so. And there is 1 mark for each of the compounds overall, giving us 2 marks for this part of the question. Now, as we've identified, our reaction 2 gives us a mixture of the compounds. And we've identified that compound A is the major product. And now we need to draw a mechanism for the formation of compound A overall. And we need to ensure that we're using our curly arrows and that we're showing any relevant dipoles here for this question. So let's start out by drawing our MAC compound, and then we can start to add in some curly arrows and some dipoles to follow this reaction. So this is going to be reacting with HCl, and this is an electrophilic addition reaction where our HCl is acting as an electrophile, and the reason why is because the chlorine is more electronegative than the hydrogen, therefore generating a permanent dipole where we've got our partial charges on these atoms. Therefore, the slightly positive hydrogen is going to be attracted to this electron-dense double bond region over here. And it's an addition reaction because we're adding onto that double bond. We're opening up the double bond and adding new bonds in overall. So let's start to look at some curly arrows now. So for our curly arrows, we need to identify the source of our electrons and then where those electrons can flow onto. And each curly arrow with a double arrowhead represents the flow of 2 electrons overall. So our source of electrons is going to be this electron-dense double bond region here. And they are going to flow onto that slightly positive hydrogen. Now this is going to form a bond, and hydrogen can only form 1 bond overall. Therefore, the bond between the H and the Cl is going to break. So that electron pair is flowing onto this chlorine. The electron pair is already slightly closer to the chlorine anyway because the chlorine is electronegative. And it's important in our diagrams that our curly arrows are going from the direct source to where we want them to go. So we have to be really clear with each end of the arrows and where those are flowing to. This is then going to generate our intermediate, which we drew above, but we're going to draw it again here so that we can then add in the rest of our arrows. So we've added on our hydrogen to this carbon here. So we've got a carbon with 3 different hydrogens. And then let's draw in the rest of our compound. And then now we've got an electron deficient carbon. We've produced a carbocation here because this carbon has now lost its bond here. It's lost these electrons. Therefore, it's positively charged. Now, what we also produced in this section was a chloride ion when we flowed these electrons onto this chlorine. So we've now got a carbocation, we've got a negatively charged chloride, and this is going to therefore attack that carbocation there. So those electrons are going to be flowed onto that carbon, forming a new bond. And therefore, we're going to produce this compound here. And this is going to be our major product because it's gone via the most stable intermediate, the most stable carbocation, which is the tertiary carbocation because the carbon has got 3 other carbons bonded to it, making it the most stable. And for this question, there was a mark for drawing the first arrow here from the double bond to the hydrogen. The second mark was for drawing the dipole on the HCl and for drawing this second bond here, which was breaking the bond between the hydrogen and the chlorine. And then the third mark was for drawing your curly arrow in this intermediate here, showing that chlorine going to that carbocation overall. Explain why compound B is the minor product of reaction 2. So reaction 2 was the electrophilic addition of HCl to our compound MAC. And our minor product was the one where the chlorine was bonded to carbon number 1. And the reason why this was the minor product was because it went via the least stable intermediate. So it's because it had the least stable carbocation intermediate overall. And you need to say all of those points in order to get this mark for this question. Now we are told that MAC reacts with water in the presence of aqueous silver nitrate and ethanol. And for this question, we need to draw the structure of the organic product, state what we would observe in this reaction, and identify the compound responsible for the observation overall. So with our compound MAC, this has got a chlorine atom overall. And when we react it with water in the presence of aqueous silver nitrate and ethanol, we're going to get a hydrolysis of this bond here, and therefore we're going to get a substitution where the chlorine is replaced by a hydroxide ion, therefore giving us this compound here as our product overall. So we've just substituted out the chlorine with a hydroxide overall. And what we would observe would be a white precipitate overall. And that is because when we get our hydrolysis of this bond, we're going to produce some chloride ions. And the test with our silver nitrate is the test for chloride ions. And that's because you get a reaction between these, a precipitation reaction, where we produce silver chloride, which will be that white solid, that white precipitate. And for this question, there was 1 mark for the structure of the organic product and 1 mark for identifying that we've got a white precipitate as our observation and that the compound responsible for this was silver chloride. So you need both of those last points in order to get that 2nd mark overall. Compound A reacts slowly in humid conditions to form compound C. We are told that compound C contains the following percentage composition by mass. So we've got 46.1% of carbon, 7.7% of hydrogen, and 46.2% of oxygen. We are also given an infrared spectrum of our compound C, which is shown here. And for this question, we need to use all of this information to deduce what the structure of compound C is overall. So the first thing to note is that we've got humid conditions. So this tells us that we've got some source of water, which is going to be a source of oxygen and hydrogen. So that's something to bear in mind here when we're thinking about our compound C, which only contains carbon, hydrogen, and oxygen. We can now look at our percentage compositions by mass because we can use this data to work out the empirical formula of compound C overall. So let's start by setting us up a table. So we'll need our percentages, our moles, and our ratios. And because we've got the percentage composition by mass overall, we can use the formula of moles equals mass divided by atomic mass. So where we're using our percentages as the masses here for each of these parts overall. So let's start by filling in our percentages. So we've got 46.1% of carbon, 7.7% of hydrogen, and 46.2% of oxygen. So now let's work out the moles of each of these parts. So for carbon, we need to divide this by 12, which will give us a moles of 3.84. For hydrogen, we need to divide this by 1, which gives us a moles of 7.7. And for oxygen, we need to divide this by 16, which gives us a moles of 2.89. And all of these atomic masses can be found in your periodic table in your data booklet overall. So now we need to work out the ratio of each of these atoms to each other. And we can do this by dividing each of the moles by the smallest mole value. So we need to divide each of these by 2.89 in order to work out that ratio. So when you divide each of these values by 2.89, you get a ratio of 1.33 for carbon to 2.66 for hydrogen to 1 for oxygen overall. Now, for our empirical formula, we need to have the simplest whole number ratio. And we haven't got whole numbers here, but they're also a little bit too big for us to just round up and down. But what we can see here is that we've got some form of a third here. So if we times these all by 3, we could potentially get to some whole number values. So if we now times each of these by 3, we come to values of about 4 to 8 to 3 overall. So therefore, our empirical formula is going to be C4H8O3 for our empirical formula. So now, let's take a look at our infrared spectrum of compound C. And there are a few key peaks in the spectrum which we can point out. There are 3 peaks here which are standing out. And we can remember that everything between around about 500 until 1500 is going to be our fingerprint region. So we can't actually identify any clear peaks from this region because it's quite noisy, it's quite messy, but each individual compound has its own unique fingerprint region, like a fingerprint itself. So now, if you use your data booklet to look at the transmittance and the wave numbers, so the different wave numbers for these peaks, we can identify this peak here, so this is the peak at around about 3,450. This is going to belong to the OH from an alcohol overall. We've also got this broad absorption between about 2,500 and 3,300. So this is a broad absorption, which is key. And this is going to be the absorption which belongs to the OH from a carboxylic acid functional group overall, so from this OH here instead. And finally, the other peak which stands out is this sharp absorption here. So this is between around about 1,640 and 1,750, and this is going to belong to the carbonyl bond from our carboxylic acid overall as well. So it's time to put all of this information together now. So looking back at our empirical formula, when we compare this to our compound A, they've got the same number of carbons. So therefore, a good deduction to make would be that this also would have the same number of carbons, hence this is also going to be our molecular formula. So if we draw in our carbon framework then to start us off, we're sticking with the same number of carbons, it's humid air, so a good deduction to make would be that our carbon framework won't be affected too much. And now we identified from our infrared spectra that we've got a carboxylic acid functional group and an alcohol functional group. And that totals up to 3 oxygens in total. So we've got 2 from the carboxylic acid, 1 from the separate alcohol, and that matches up with our empirical formula over here. So now it's just time to tie all of that together for an overall structure. So it would be a sensible deduction because our original compound contained 2 chlorines, but compound C does not contain any chlorines. So these are probably going to be the areas which have changed in terms of where we're replacing the chlorines with our new oxygen-based functional groups. So we could put our alcohol group up here. So we're just substituting that chlorine out for the alcohols. That'd be a substitution reaction. And for this section here, to turn into our carboxylic acid overall. So this would give us a final structure that looks like this overall. So just adding in our atoms and then the rest of the hydrogen atoms. And let's just count up and check that we've got the right number of hydrogens. So we've got 4 carbons, we've got 3 oxygens, and for our hydrogens, we've got 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 hydrogens in total. And for this question, there was a mark available for the ratio, a mark available for the empirical formula. There was 1 mark available for identifying the alcohol absorption in the infrared spectrum. And then for the 4th mark, we had to identify the absorption from the OH that belonged to a carboxylic acid and the absorption belonging to the carbonyl bond for the carboxylic acid. So we had to have both of those mentioned for the 4th mark. And then the 5th and final mark was for the structure overall.